So I'm going to take you through C2 using some examiner's comments from last year. So first of all, people didn't know that nitric acid was the acid used to make ammonium nitrate. Now there are two things that you need to think about here. The first of all is nitric acid makes a salt with an ending of a nitrate. So nitric acid makes a nitrate. But also you need to know about these ammonium ions. If you're using nitric acid, you make nitrates, sulfuric acid, you make sulfates, and hydrochloric acid, you make chlorides. But also remember that on your formula sheet, you've got the formulae of all these ions. Now this is an ammonium ion here, NH4+. So if ammonium reacts with a fluoride ion, then there's just one of them joined to F. And the whole ammonium ion joins to the whole nitrate ion to make ammonium nitrate. Ammonium joining to sulfate. Now sulfate has a 2-, so you'd need two of these NH4s, that should be subscript, to join to our SO4- here, SO4 2-. Really with the formulae of ions, it's the same as all the other formulae that we looked at. So Mg2+, you balance that out with an O2-, whereas if you've got an Mg2+, then you need two Cl- to balance it out. So you need two of those minuses to balance out the 2+. Okay, so the next thing is electrolysis. Students didn't know that the other part of the mixture used to produce aluminium in electrolysis is just aluminium oxide. So you dissolve aluminium oxide in cryolite. Now it's really important here that when you're talking about electrolysis, you don't talk about bauxite or aluminium ore. You specifically say that it's aluminium oxide. So here we go. Here's a typical question here. So aluminium is manufactured by the electrolysis of molten mixture of cryolite and that would be aluminium oxide. This is the mark scheme here. And if you look, they've said ignore bauxite or aluminium ore. You have to be specific about the fact that it's aluminium oxide. And this is our typical setup here. So we've got molten cryolite with aluminium oxide there, which means that we produce oxygen gas as well as forming aluminium metal. And in general with electrolysis, you've got to know what happens at the anode and what happens at the cathode. So the anode is the positive electrode, cathode is the negative electrode, and you've got to be able to talk about how things lose or gain electrons. The other specific example they mention here is the electrolysis of sodium chloride. People tended to know that you form hydrogen, but then they forgot the other products, and you have to know these. So again, pause this and have a look. Because of the ions that you've got floating around here, you get sodium hydroxide produced, and you need to know the kind of things that you use sodium hydroxide to produce. Chlorine is made and hydrogen is made. Chlorine is used to make bleach, hydrogen used to make a fuel, or hydrogen used as fuels, and then sodium hydroxide are kind of soaps. But also have a look again at this aluminium oxide. Here again we've got the purification and silver plating, so pause this, have a look at this card. Because the other thing that people didn't always know is the properties of silver that means that it's used for electroplating. So this spoon that we've talked about a lot this year, if we're electroplating something with silver, why do we do that? While we're on this question here, it's worth just pointing out another couple of things. So this is the difference between high density polyethylene and low density polyethylene. Now it says here they're made from the same monomers. So in C1 we talked about the monomers making polymers. Here we're talking about how polymers can be different once they've been made. It says how can the same reaction produce two different products? And if you look at the mark scheme here, these are just worth noting down. So you could have different conditions, different catalysts, different pressure, different temperature. The thing they don't have is different monomers. So it's the same polymer, but you just use different catalysts or conditions to get the different densities. And this is another question that people misunderstood. So the question asks you to give 2 reasons why instrumental methods of analysis are used to detect impurities. Now the question here is about instrumental methods. It's not about impurities in metals. So some people wrote about the impurities in metals, but what they wanted was why it is that you use instrumental methods above things like, so the burettes that we looked at in the previous bit. So these are the 4 that they're looking for. They're accurate, they're sensitive, they're rapid, they're fast, and you only need a very small sample. The next thing that people weren't very sure of was their oxides and bases and alkalis. So a metal oxide is a base. If this metal oxide dissolves in water, if it's soluble, then it will make an alkali, because the oxide turns into a hydroxide. And remember, it's the OH minus, the hydroxide ions, that make something an alkali. Then if we've got our acid containing H plus ions or an alkali, they can neutralise. You have a neutralisation reaction. They join together to make water. You've got to really think about the language you use as well. Things aren't lightweight. We're talking about density, low density. And if you're talking about properties of shape memory alloys, for example, make sure they are specific to that shape memory alloy, not just the properties of an alloy in general. So let's just have a quick summary here of, so these are the polymers. Remember, it's many monomers joining together. We've got thermosoftening polymers, we've got thermosetting polymers, and then we've also got the different densities, low density, high density, and this gives different properties here, so you've got to know all about these. So just pause for a minute if you need to and just check that you're happy with these. Also the metals and alloys, so we've got this idea of alloys which can't slide. We disrupt those layers or we distort those layers with different elements or different atoms there. We've got the shape memory alloys. They return to their original shape by themselves. So a good example is in dentistry for braces. And remember, when you're talking about the structure of metals, don't just leave a diagram unlabeled. Make sure we've got ions surrounded by delocalized electrons, and it's in a lattice structure. Also, think about how you answer things. If they're asking you to compare things or say why something has changed, you need to use a comparison there. Don't just quote the data. So this is an example. What effect does the temperature have on the rate of reaction? Well, you can say that more gas is given off more quickly at 40 degrees than at 20 degrees. You've got to say something about 40 compared to 20 to say that the temperature has an effect.